Hey guys, welcome. In this video, I'll be showing you how to make your own NFT marketplace because there's not enough out there already. You might be like, what about OpenSea or Rarible or Foundation and all of these cool marketplaces that are already out there? And my answer to that is, they're cool, they're fine, but they're not ours. We want to make our own because, well, money. And also because I found that learning by building is probably the best way to learn, at least for myself. So in this video, I'm going to try to teach you the basics of Solidity and smart contract development, while at the same time building something practical like an NFT marketplace. And also we're going to set a very ambitious goal for this video. If this video gets 1,000 likes, I'm going to make a follow-up video to this. And in that, we're going to take whatever we build in here and expand on it, make it even better, just make it more complex, add more features. And in that video, I'm going to set another goal and so on. We're going to carry on like this until OpenSea is out the game. It's a closed sea. So the first thing we're going to be needing is Node.js. So just go to Google Node.js, go to the official website and download one of these two versions. I'm using 17, but you can go 16. Either one is fine. Once that's downloaded and installed, go and open up a terminal window and type node -v. And here you should get the version that you just installed. If you get some sort of error or something else, then Node is probably not installed properly and you need to somehow figure that out. But once that's done, you can just move on to your code editor. I'm using VS Code. And let's create the new project. So go to your location and create a new folder. I'm going to call this NFT Marketplace for a lack of more creative name. Open it and we should have it here. So now it's time to just open up a terminal again. You can do that inside VS Code if you go to terminal, new terminal, or press this shortcut. Anyway, in the terminal, just go npx truffle and init. Now, Truffle is a library that we'll be using to compile our Solidity contracts and then deploy them to a network. And by running the command that we just ran, it's going to create a few directories and files that will help us out quite a bit. But first, just go to truffle config and start getting rid of most of this code because we won't be using it. We need to keep this one, get rid of this, comment this in. These comments are kind of useless. And by the way, we can get rid of the Docker. Finally get rid of, this one. So in the end, you should be left with just these few settings. Yeah, so we're good to go. Now, let's go to our contracts directory. As you can see, this already has this file called migrations, and inside there's this contract called migrations. And you don't really need to worry about this. It's just a thing that Truffle creates to keep track of the different deployments. But so let's create a market contract. So new file into contracts directory, market.sol. You can name it whatever you want, but the extension needs to be .sol. Okay, so in here the first line needs to be SPDX license identifier and then a software license. We're going to keep it to MIT. You'll probably find that most contracts are MIT, but I mean, there's a whole thing about licenses that you can learn about, but we're just going to stick to MIT for now. The next line is going to be Pragma Solidity and then the version of Solidity we want to use. In this case, I'm going to be using the latest one, which is 0.8.9 and then semicolon. You can see what the latest version is going back to Chrome. Go to the website and under here you can see the latest one, which is 0.8.9. Okay, so once you have decided on that, let's go back into our config and change our version over here to match that. So we're going to change it here to. There's another thing I want to show you. If you're using VS Code, I recommend going into your extensions and downloading this extension called Solidity. As you can see, it has almost 500,000 downloads. and it has some cool features like syntax highlighting, snippets, and all this stuff. Anyway, moving on, you can go here, contract, market, and then open curly brackets. The name here, I've made it the same as the file name, but it doesn't have to be the same. This can be different from here, but it's just a good convention. Why not just make it the same so you know exactly what's what? So now everything we create will go inside these curly brackets. So let's begin. First of all, what do we want our market contract to actually do? So we want to allow sellers to list their tokens, create listings of their tokens. And secondly, we want buyers to be able to buy those tokens. And the third functionality we want to add is for allowing the seller to cancel one of his listings. Let's say he changed his mind or his tokens aren't selling, so he just wants them back. So that's the three things this contract is going to handle for now. Let's begin by creating a function. So just type function, and then the name of the function in this case will be list tokens, token, create listing. I say list token will be better. So we have this, and then public curly brackets. Now, what is this public? This thing is what we call our visibility modifier, and there's 4 different options. So the first one is obviously public. So what this means is that anyone can call this function. A contract, a wallet, anyone can basically interact with this specific function. So anyone can call. Second, we have private, which is, well, the opposite of public. And if we make this private, what that will mean is that only this smart contract, the market smart contract, will be able to call this function. Essentially, if we create another function, let's make this public or whatever else. Now, list token can be called by this function, but it can't be called through, let's say, MetaMask or another contract. Then we have internal. This is very similar to private, except it allows inheriting contracts to also call a function. So if we make this internal, now we can create another contract called, let's say, market plus, and this inherits from market. So market plus is essentially a market, but it also has some new cool feature. And if you make list token internal, this function will also be able to call list token. But if this is private, market plus will have no access to it. Only this contract and inheriting contracts. Finally, we have external. Now this is quite similar to public, except public can be called by anyone. So even this extending contract, our own contract. But if we make this external, as you can see, our contract won't be able to interact with it. Only external contracts. Now, only if we create another contract that will be able to access this function. Our own market contract won't be able to. So as you can see, another function has no access to this. So only external contracts. Actually, only external calls, because this can still be called by our wallet from, let's say, MetaMask. So let's just get rid of this and get back to our list token function. Now we need to define what a listing is. So we can create something called a struct, and we're going to name this listing. This is going to be what the actual listing that the seller creates looks like. So it's going to have the token, right? What is the token that we're listing? And this is going to be an address. Yeah, so this is going to be the address to the token contract. Then we have, this is going to have a semicolon. Then we have the ID of that token ID, and then the price, uint price. Now, when the seller calls this function, we want to create something that looks like this. So here we have listing type, and then the name of the variable. We're going to keep it listing, but this can literally be anything you want. I'm going to call listing equals listing again. So semicolon, and in here define what the token is, token ID and price. But first, as you can see, you get an error over here. It says data location must be storage, memory, or call data. Now I'll get to this in a bit, but for now we're just gonna keep it as memory, as that's really the only one that we can have over here. If you try something like storage, it won't work. Even call data, we get the same error, it's not going to work. So we're restricted to memory anyway. Now listing wrong argument count, of course we need to pass in what the actual token is, what the token ID is, and the price. And we're going to receive these as arguments from the caller of this function. So we want to make address token, we need the address, we need the token ID, which is going to be uint token ID and uint price. Now, what is uint? Uint means unsigned integer. If you have a computer science background, you'll probably already have figured this out. It's essentially an integer. That's all you really need to know. So it's a whole number. You can learn more about the details on the Solidity website. We can't have floats or doubles in Solidity. We're restricted to just ints. We can have different sizes. 256 is the standard, and that's actually what uint on its own actually means, but we can have smaller ones, although most contracts will stick to uint 256. Anyway, moving on, we pass these parameters, we pass these arguments to the actual listing type, token ID, and price. There we go, we've created this listing and it's in memory. What memory means in this case is that this listing variable that we're creating will stay into memory for the duration of this call to this function. So this specific function call will have this variable, which is pretty much what you're probably expecting anyway. Okay, so we've created listing for this function call, but how do we actually store this listing and persist it for other ones? I mean, we don't really have a SQL database or any database for that matter. Instead, it's actually a lot simpler. So all you have to do is just go here outside the function, create a mapping. And inside the mapping, we're going to have a uint that maps to a listing. And we're going to call this listings. Very creative. And we can also make this private. It doesn't need, actually should be mapping private listings. The visibility modifiers for the fields are pretty much the same as the functions, except for external, which doesn't apply to these. And listings, we're going to append a underscore at the beginning of it. This is just a convention. It doesn't have any technical consequences. It's just a standard way to name private variables so that we know that they are private. What mapping does is it takes an integer and then matches that to a listing, and this will be stored forever. So in here we can go listing underscore actually listings, and then we pass in a integer. For now, let's say 1. And then that equals to listing. This is the listing that we just created here in memory. Now this integer, where do we get that from? So we need each listing to have a unique ID. So we're going to make an incremental counter. We're going to have uint private listing ID. Again, we're going to prefix this with an underscore. I'm going to initially set it to 0. And each time we create a listing, we're gonna increase this, and we can just do double plus sign, and this has augmented this value. So listing ID plus plus means listing ID is now 0 plus 1, and then we set that listing ID to this listing we have created. I mean, pretty simple so far, right? We don't need to deal with any SQL database queries and repositories and all that stuff. You just throw it into a mapping. That's literally it. Now, every time a new listing is created, it will first increase the listing ID and then set that listing ID to the new listing. Okay, now we can move on to the actual buying functionality. So function buy token, and here we pass in a listing ID. The user will tell us which ID listing they want to buy, right? So we can also make this external, because we're not going to be calling it from inside our contract. Only external calls will be handled. So we go into listings and then pass in the listing ID. Now we have access to that listing, and we're going to store it into a variable listing, call it listing. Now here again, it says data location must be storage, memory, or call data. Now in this case, we can use storage. What this will do, it will create a pointer to the listing that we have inside of this mapping. If instead we use memory, what will happen is the listing that's stored in the mapping over here will be copied into this function, into this variable, and then we can access it and make changes, but these changes won't be reflected and persisted into the actual storage. Now, if we want to apply those changes, what we'll need to do is do listings, listing ID, and then set that listing to this new listing that has been modified. But instead, why not just use storage? Now that's a direct pointer to the listing in this mapping, and we can just make changes here, listing price, and they will be updated. Okay, so now before someone buys a listing, we want to make sure a few requirements are met. For example, we want to verify the payment. We also want to make sure that the seller is not buying his own listing, right? Because that wouldn't make sense. And to do that, we first need to store who the actual seller for a listing is. As you can see here, we don't know who the seller is. Once that's created, it's created. We don't know who it is. So how about we just add address of the seller? And now when we create the listing, we can add it here. But we won't be adding the seller here in the parameters, because this can be easily, you can set this to anything, right? We want the seller to be the actual person that's actually making that transaction. And to get the address of the actual caller, we can use msg.sender. Now MSG is a object that's injected into each function call, and it has some quite useful information like the sender, the guy who's actually making the call, and that's also going to be the seller in this case. So we set the listing seller to message sender. And another thing we want to add to our listing is the status. And to do that, we can use something called an enum. So we create a new enum called listing status, and this can either be active, sold, or cancelled. Here inside the struct, we can just use that type. So listing status is status and then semicolon. And when we create the listing, we can go here and listing status, and it's initially going to be set to active. Okay, so going back to our buy function, another thing we want to check is whether the listing is still active. Let's say a token has already been sold. We can't really fulfill that new order, can we? Let's make sure that the listing is still active. So we can use something like a typical if statement, listing.status is equal to the type listing status dot active. Actually, if it's not active, then we can do revert. Revert will just cancel everything that comes after and return an error message that we can specify here. Listing is not active. Yeah. Or we can do something a lot more cleaner, which is we can use require. Require is a function that Solidity provides, and it pretty much does exactly this thing over here. So instead of making sure the listing is not active, we make sure that the listing is active. Require that the listing is active, and if it's not active, return this error message, and we can get rid of this. Now anything that comes, if the listing has been sold or cancelled, anything that comes after this won't be executed. Now let's make sure that the seller is also not the buyer. So MSG sender is not equal to listing dot seller, and the error message we're going to return is seller cannot be buyer. We can place it at the top over here actually. Now the next thing is we want to accept a payment for this buy token. Like if someone wants to buy the token, they have to pay this price we have set over here, and we do that by adding payable over here. So by adding payable over here, we're allowing the user to send ether to this function, and we can access the amount that they've sent through msg.value. The value is the value of ether sent with this call basically, and it's going to be in way. If you're not familiar with Ethereum, Wei is just Ether, but a lot smaller. So 1 Ether is going to be equal to this many Wei. This is actually 18 zeros. Okay, so we also require this to be greater than or equal to the listing dot price. If it's not, we return the error message insufficient. Give me some ideas. Insufficient payment. Yeah, whatever. Okay, so now we have all this in place, but how does the exchange actually happen? The exchange of tokens. The way we handle that is when the seller decides to list his tokens and calls this function, passes in these parameters, we actually want to deposit that token into our own contract. That way, when the buyer buys it, we have the token for sure and we can send it to them. If you just leave it in the seller's hands, we don't know if it's going to be available when this person over here calls buy token and sends us 1,000,000 Ether. So before we create this listing, it's necessary that we take in that token. The tokens that we will be supporting will be of ERC721 standard. We're going to create another file. We're going to call it IERC721.sol, and then in here we're going to copy these first 2 lines, paste them, and in here we start this one with interface IERC721. Now the standard, the actual contract will be called ERC721. This I just symbolizes that this is an interface. We could remove it and just call it whatever, but it just helps having an I to see, get it? Cause like, well, it just makes it easier to identify whether a thing is a smart contract or an interface. We can import that using import, and then the path we can do IERC721. So now an interface is just a description of what an actual implementation will do. So we can define the different functions. Let's say hello. So now when we create an actual ERC721 token, so contract ERC721 is IERC721, this contract will actually have to implement this function. If it doesn't implement it, we will get an error. Say function, say hello. Let's make it external or public. Now, as you can see, the error goes away. But if we change it, we get the error again, because this implementation has to follow this interface. So you can give this interface to someone and they'll know exactly what they can do and what they can't do. So now let's just remake this valid again. And if we go back into our market contract and type IERC721, we can for sure call say hello. It's just guaranteed. We can definitely call say hello because that's what the interface requires. And in here, we'll have to pass in the actual address of the contract. So in this case, it will be the token address that we have over here. It's an address, we cast that address as our IERC721 token and then say hello. Of course, this isn't our real function we want, so let's just get rid of this. And we can see the actual functions that we require by going to IERC721. And as you can see, this is a GitHub link to Open Zeppelins. Now we don't need all of them, we just need this one over here, transfer from. We can copy it here. So now we know that this type of interface will have a transfer from function, and we can pass in the from, which will be the MSG sender to address, to our own address, to the address of this contract, our market contract, and we can get that by saying address this and then the token ID. Now we know that this is going to be working because IERC721 is a widely used standard by most NFT contracts. If we search ERC721 and look for the actual implementation, which is this one by Open Zeppelin again, and we search for transfer from, This is the actual implementation that will take care of the actual transfer. If you don't believe me, let's just check out OpenSea, for example, and we can pick any random thing from here. Let's just pick this one, go to details, contract address, go to contract which has been submitted and has been verified, as proven by this check mark over here. And if we scroll down, we can see that this NFT is actually a ERC 721 smart contract. So if we search for transfer from, let's search in here the actual. So if we search for transfer from, here you can see the actual implementation again. So we can be sure that actually all the NFTs that follow this standard, we can transfer them and they will work with a market contract. So going back to our code, we're taking the token address and calling this transfer from function. Now going back to our visibility modifiers, as you can see, this would need to be external or public. That's the only way we can call it from our own contract. And now then we pass in the from is the actual seller to our own contract token ID. This token from this seller inside this contract will be transferred to us. Now you may be saying that the ERC 721 interface that we have here doesn't have all the methods that the actual implementation has, and that's perfectly fine. I mean, the interface just means that at least those functions that we have specified in the interface need to be included, but the contract can choose to implement more if it wants. In this case, we have the transfer from, which is the only one that we're telling our market contract about. That's the only one it needs to know about, and it works. It's all we need. So we're gonna copy this transfer call and paste it here. When someone buys the token, what we do is listing.token, we get the same address, and then in this case we transfer it from ourselves, so address this, and to the buyer, which is MSG sender in this case, and then the listing.token ID to get the token ID. There we go. Now we also need to pay the seller because we have the money from the buyer, and we need to pay the seller because otherwise that would be kind of unethical. Now we can take the address of the seller. We know who the seller is through our listing, and we go transfer, and we can send MSG value. No, actually we don't do MSG value. Instead we do listing.price, because as you can see here, the MSG value can be higher than the listing price, but we only want to give the seller the actual price that he asked for. But as you can see, we have an error, and it says send and transfer are only available for objects of type address payable. Now this is an address, but it's not a payable address, and to fix that we just cast this as payable. Now that's a payable address and we can send it money. Now again, see, like here the external call is made at the beginning, because as I said, we want to take in the stuff first because we don't trust anybody else. But when it comes to giving stuff, we give it at the end. So always take in stuff first and give stuff afterwards. Now to summarize, we have a list token function which allows a seller to deposit his token inside of our contract and create a listing. And then we also have a buy token function that our buyer can call, pass in some ether. We mark the listing as sold and we transfer the token to the buyer and the payment to the seller. So that's an exchange we facilitate through this contract. Then we also need a function, like I said earlier, that allows the seller to cancel. Here once again we're going to pass in the listing ID. We can make this external or public. Let's just make it public, and brackets. Now we get the listing, so listing storage listing equals listing ID, and then we want to check if the listing is even active. So require that the listing status is equal to listing status active. If it's not, we return the error message, which is listing is not active. And we also want to make sure that the canceller is actually the seller. So MSG sender is equal to listing.seller. Only seller can cancel listing. There we go. We can actually make this first. Now we mark the listing as sold. Go back up. Listing status equal listing status dot sold. Cancelled. It's cancelled. Now that's been updated, and only now we make the external call, which goes like this: listing token transfer from address this. We transfer it from ourselves to the message sender, which in this case is definitely also the seller, and that should be it. We have a pretty cool contract now that does buying, selling, and cancelling. So this is a fully working contract that does exactly what I said it will do in the beginning, but there's a few things we could add. For example, events. Events are what I'll show you actually. So if we go to Etherscan again, if you go to Etherscan and let's look at this contract that we opened earlier. If we go into transactions and we open something from here, let's say this transaction over here, any of these, we can go into logs and you can see this over here, approval for all. This is actually the name of an event. If we go back into our ERC 721 implementation, if we search for approval for all, we can see here, yeah. So someone called this approval for all function, and this is emitted. Emitting events is completely optional, but it can be nice to like see what's happening inside your contract. So if we go into these other transactions, this one for example, we can see there's 4 events being emitted. One of them is sent, transfer, transfer with data, and transfer. These are just different variations of the transfer event in different places of the code. So it just gives you a clear understanding of what's happening here. We can create one of these events when someone lists a token. So we can call this event listed. And in here, we can have the person who listed the token, so the seller, the token address, which NFT contract we're talking about, the actual token ID, that could be useful, and maybe even the price, that would be nice. I'd say even the listing ID could be nice to have, listing ID. This is just information that you might think could be useful in the future. We can emit this event now when someone lists a token. So down here we can go emit listed, pass in the listing ID, MSG sender, which is the seller, token ID, and the price. And by the way, talking about price, let's make something clear. Price, like I said here in the buy function, this will be passed in as way. This needs to be the same over here when listing the token. So you can't just pass in 1 and expect it to cost 1 ether. The price here will correspond to the price in way, not ether. We could do something like price times 1 ether. So this price will always be in ether, but that can be a problem and you might not want to do that, because let's say if someone wants to list something for half ether or 0.0001 ether, they can't do that because everything's going to be times by 1 ether. 1 ether is of course equal to 1 followed by 18 zeros, so that's a big number. And the reason why that's so big and the ways are so small is because we want to allow transacting with very small amounts. Let's say we have 0.001, we can't have floats and doubles, so that's why we have such a big number to deal with such small amounts, if that makes sense. So we want to leave this as price, but whenever we're calling this function, we want to pass in ways and not ether. And another event we might be interested in is event sale. This will be emitted when someone buys a token. Emit sale. And what are the different things we might be interested in knowing? I don't know, like UINT listing ID again. We want to know what the listing was, who the buyer is, what the token was, what the token ID was. Actually here we need commas, by the way. Price, I mean you can add whatever you think might be useful. You don't have to follow a specific standard. So listing ID, buyer, token ID, and price. Actually I think that's fine. So in here again we do listing ID, MSG sender, token, which is listing token ID, and then the price, listing price. This, of course, this needs to be uint, and might as well add an event for cancel as well. So event cancel uint listing ID and the seller. I think that's enough. You don't need much else. I think emit cancel listing ID and listing or seller. Yeah, that's pretty much it. Now we also have events. Looking nice. So there's just one more thing I want to add, which is function get listing. This will, as you can probably guess by the name, it will return a listing object, this thing over here, given a listing ID. When we want to return something from a function, first we put the modifier, visibility modifier, which in this case we can make it public, and then we do returns, and then in brackets we put what the actual thing it's returning. In this case it will be returning a listing, or this could be a uint string bytes 32 usually, but let's just put listing here, open curly brackets, and then here we can do return listings and listing ID, and we get an error message, and it says data location must be memory or call data. Okay, so we haven't covered call data yet, and all I'm gonna say in this video is that it's very similar to memory, only it can't be used inside this function, only for the parameters here or in this return thing over here. But in this case we're gonna do memory and listing, or we can actually remove listing. If you were to put listing over here, you could simply do this. But in this case, it's not very useful. If you are dealing with different variables with different names, it could be a bit more useful, but in this case, it looks nicer if you just do this and do this. Now we get this yellow squiggly line, and if we check what it says function state mutability can be restricted to view. Now state mutability is another thing. In this case, we can restrict this to view. What that means is, okay, so there's 3 different options, I think. Well, I'm going to cover 3. I think there's 3 anyway. So view, so we have the normal one, right? There's nothing basically. What that means is the function can read and write. So for example, this is a normal one, and we have listing. We access it from storage, so we're reading, but then we're also changing the status of it, so we're writing. So then we have view can read, not write, so read only in this. So for example, here we're accessing the listings mapping, and we're returning one of the listings, but we're not really making any changes to it, so this can be restricted to view. And then there's also a third option, which is pure, and what that means is you don't no read, no write. And you may be asking, what's the point of that function? I mean, you could have something like sum uint a, uint b, and you could just return a plus b, public pure returns. There we go. So this doesn't read anything from the contract, and it doesn't write. And the thing about view and pure functions is that they can be called, and it doesn't have to be a transaction. So you can call them without passing in any gas fee, so it's completely free to call them. Whereas these functions, buy token, list token, you would need to send some gas, and that would cost you. But get listing, you can call it as many times as you want, and it will be completely free because you're not writing anything. You're paying if you're writing something to the contract. So I'll get rid of this, and now we have this function too. Also, just wanted to mention something very quickly. I made a Discord server since my last video, so if you're facing any issues or have any questions, feel free to ask them there, and I'll try my best to answer them, and we will all just try to help each other out, right? Yes. And by the way, you don't have to pay for it or anything. It's completely free, and it's not like an exclusive. I mean, it is an exclusive, very exclusive group, but you don't have to pay for it, so it's completely free. And this is looking pretty good to me. So I think we're done with the coding for now. And the next part is actually testing the contract, which is very important. Of course, testing is important for all software, but it's especially important for smart contracts, because as you may be aware, once the smart contract has been deployed to the blockchain, you can't make any changes to it. It's immutable. But let's say you made a mistake, and it can be quite expensive redeploying to Ethereum mainnet if that's what you're aiming for. I mean, you might be paying around $200 each time you make a change. So you want to test it locally as much as possible, and only then first you throw it onto a testnet and then onto the mainnet for Ethereum or for whatever network you want. For now, what we're going to be doing is we're going to compile this contract and deploy it locally. And so let's open the terminal. Let's do npx truffle compile. So by running this command, Truffle will take the Solidity that we wrote and compile it into bytecode for the EVM, which is what the Ethereum network uses. Now we can go into this migrations file, the first one, and then we go const market artifacts require, and then the name of our contract, which is market. In here we go deploy market. So these migrations are just a series of steps Truffle will take to deploy the contracts. Now let me show you something else. Let's jump back into our terminal, and let's use a library called Ganache. So npx ganache -cli enter. Now we have a local blockchain running. So this is basically what Ethereum is, but it's running locally. Now we can just take this contract we wrote and deploy it onto here and see how it will work on a real blockchain. So let's just split this terminal, or just create a new one, and do npx truffle migrate. Now this will take the compiled contracts and deploy them onto the local blockchain that we have running here. Now, how do we actually interact with those deployed contracts? We can do npx truffle and console. Now we're going to be inside this, and we can do const m, you can call it whatever you want, and then await market.deployed. Now this will take the instance of the market contract that we have deployed to Ganache and store it into the variable m. Press enter, and now m get listing, passing the 1. And as you can see, this returns a listing, but it's all set to 0. So the thing with mappings is that you can pass in any integer here and you'll always get an object. Every key exists, but the thing is, it's probably going to be set to 0. So how about we create a listing? So list token, we have to pass in an address. We can get that from accounts 0, which is just a variable that Truffle injects for us. Then we have token ID 1, and then a price, which is, let's just set it to 100. And we get this error message, and the reason for that is we don't really have a token with the address that we gave it and the token ID that we gave it. So when it runs transfer from, that just fails because we don't have a token. So how about we just create a test NFT contract? So let's just go into our contracts again, NFT sol, copy these 2 lines, contract, let's call it NFT, very creative name. And then this is going to be an ERC721. Now we don't want to implement this IERC721 interface that we wrote, because then we would need to implement all the different functionality. Instead, what we're going to do is we're going to use an existing contract, and we're just going to extend that. And to do that, we can just use OpenZeppelin, the contracts that we were looking at earlier from GitHub. So if we go to a browser here, we can use one of these. We can use this contract from OpenZeppelin, and what Truffle allows you to do is that instead of having to basically download that and have it and save it in here, we can just do npm install OpenZeppelin contracts. Okay, so now we've installed that library that OpenZeppelin provides. Import, then OpenZeppelin contracts. I can't remember the exact path, so we can just go into the browser again, and contracts token ERC721, ERC721. And there we go. Now we get an error message, and that's because we need a constructor for this one. If you're new to programming, constructor is basically what's the first function that's executed as soon as that class or instance is created. In this case, it's a smart contract. So as soon as that smart contract is deployed, we can put code here that will be executed. In this case, ERC721, the contract that we're extending, already has a constructor that needs to be called. So we do constructor, but in this case we'll do constructor ERC721 and like this. Now this says it needs 2 arguments, and we can see what those 2 arguments are by going back here. And if we scroll here, constructor requires a name and a symbol. So we can go into here, we can give this a name. We're just going to call it coolest NFT, and then a symbol. I don't know, NFT, just whatever. So that's essentially a whole NFT that we have created. That's exactly what NFT is. One thing that it is missing is a mint function. So let's create that, mint, and this will be a public function or even external. We need a mint ID, private, a uint private token ID. Let's make it this 0 token ID incremented, and then this contract that we're extending has a function called _mint, and then it says who the minted token will be assigned to. We want that to be the person calling this function, making the transaction, and then the token ID will be this, and that's pretty much it. One other thing we can do is just returns a uint, and we can return the token ID. Totally optional though. Perfect. So now we also need to deploy this contract. So we go into our migrations, const NFT require NFT, and let's deploy it, NFT. Now let's go back to our terminal. I accidentally closed mine, so I'm going to do npx ganache CLI, open a new terminal, and do npx truffle compile. I could do compile to compile them all over again, or I can just do migrate, and then I can also add this reset flag. So that will make that will rerun all the migrations starting from the first one, because we could have 1, 2, 3, 4, 5 migrations. This is just going to run them all from the beginning, and press enter. And yeah, as you can see, we have 3 deployments, and these are the different contracts along with their contract address and how much gas they used and a bunch of other information. Now if we go into our npx truffle console again, we can do const t token t whatever you want to call it, t await token dot deployed. Actually, sorry, it's not token, it's NFT, the name of the contract, NFT. And there we go. So we can do t mint, and there we go. This isn't an error, by the way. This is just the logs from that transaction, and as we can see, it's been successful. So now if I do const m await market deployed and do m dot list token, I can do t address. Then what else do we need? We need the token ID, which was 1 because it's the first token, and then price, let's set it to 1,000, this token, and we get another error. And the reason for that is actually because it says it here, transfer caller is not owner nor approved. So we need to allow the market contract to move our tokens. So we go into our token and approve. Let's check the exact method. So what we need to do is check for approve. Here, so approve, first argument is 2 and then token ID. Approve the market contract m dot address and then the token ID, which is 1. Now that that's approved, let's rerun the list token function. This time it should go through, and yes, it does. So you can also see in Ganache over here, transaction gone through, there's no errors. And now we have a listing. Now we can check the listing, m dot get listing 1, And there we go, there's the details. Status 0, which is the first enum active. This will be 1 and this will be 2. This is the seller, this is the account, this is the token, this is the token ID, and this is the price. Any other integer will result in all 0 values. They don't exist. Now, if we were to test all our contracts this way, that would be a pain. That would be just ridiculous. So instead, what we can do is we can write unit tests. In here, in this directory, we'll write a few tests for our very own market contract and test out the different features like list token, get listing, all of it basically. Anyway, thank you guys for watching this. I hope you learned something new, at least one thing, maybe, hopefully, just one, like at least. I've got another video coming out soon, which will cover unit testing and deploying to different networks. We'll deploy to a test network and then to the actual mainnet. So stay tuned for that, and I'll see you in the next one.